Now we're going to look at the nature of liquids. Particles in gases and liquids flow past one another, and so they are referred to as fluids. And since the particles can flow, gases and liquids conform to the shape of their containers. But the big difference between gases and liquids is that there are no attractions between the particles in a gas. Gas particles move independently of one another, but there are intermolecular forces between the particles in a liquid, and these forces keep those liquid molecules close to each other because those are attractive forces. Increasing pressure has hardly any effect on the volume of liquids because liquids and solids are referred to as condensed states of matter. When you look at the molecules in a liquid, they are very close to each other, and there are intermolecular forces that are keeping these particles close together. So they're condensed states of matter. When you convert a liquid to a gas, it's called vaporization. This process is called evaporation when it occurs at the surface of a liquid that's not boiling. There's two types of vaporization. There is evaporation and there is boiling. During evaporation, only molecules with a certain kinetic energy can escape from the surface. So the important thing with evaporation, they have to have enough kinetic energy and they have to be on the surface of the liquid. They cannot be below the surface of the liquid in order to evaporate. When you heat the liquid, it increases the average kinetic energy of the particles because temperature and kinetic energy are directly proportional. And so if you have a higher average kinetic energy, more particles can overcome the attractive forces and evaporate. Now, evaporation is a cooling process because we're losing the high kinetic energy molecules, and that will decrease the liquid's temperature. Volatility is a measure of how easily a liquid evaporates. Acetone is volatile. It will evaporate easily and quickly. Mercury is non-volatile. It will not evaporate at all. So if I have a container of mercury sitting out, it will not evaporate. Water would be somewhere in the middle. Water would be moderately volatile. Vapor pressure is defined as a measure of the force exerted by a gas above a liquid. It's measured in a closed container, and over time, the number of vapor particles increases and some particles condense and return to the liquid state. So when we're measuring vapor pressure, we have two processes that are occurring: evaporation, which is the liquid to vapor conversion, and condensation, which is the vapor to liquid conversion. So when we think about vapor pressure, you have a closed container that only contains the liquid of interest. So over time, what happens is some of the molecules escape from the surface, they evaporate. And since there's no place for these molecules to go, once they get to the vapor phase, some molecules will return back to the liquid phase. They will condense. And over time, you get an equilibrium that exists between the liquid and the vapor. So the rate of evaporation would equal the rate of condensation, and you get this equilibrium that occurs. But vapor pressure is simply a measure of the force of the vapor that's above the liquid. So if you measure that force of the vapor in a closed container, it's called vapor pressure. I like to think of vapor pressure as the pressure that pushes up from a liquid as it evaporates. If you increase the temperature, you increase the vapor pressure because more particles have the minimum kinetic energy required to escape. And so vapor pressure will change as temperature changes. You can measure vapor pressure or gas pressure in a device called a manometer, which is just a curved glass tube. You have your gas of interest over here, and what happens is that gas exerts a pressure as the molecules collide with the walls of their container. And since it exerts a pressure, it forces this column of mercury up the other side of the U-shaped tube there. And we can measure this distance h from the volumes of mercury and get the vapor pressure of the gas in this manometer. So a manometer measures gas pressure or vapor pressure, and it's simply a U-shaped glass tube. Boiling point. The rate of evaporation of a liquid from an open container increases as the liquid is heated because the average kinetic energy increases. Now, a liquid will boil when the liquid is heated to a temperature at which particles have enough kinetic energy to vaporize. Boiling occurs throughout the liquid. Evaporation occurs only on the surface, but boiling occurs throughout. So you see bubbles forming, rising to the surface, and escaping into the air. So something will boil at the temperature at which the vapor pressure is equal to the external pressure. So something will boil when the vapor pressure equals the atmospheric pressure, which is the external pressure on the liquid. Liquids don't always boil at the same temperature. Let me give you some examples here with the boiling process. Let's say we're at sea level and we are at 60 degrees Celsius. We have a container of water. If we are at sea level, the atmospheric pressure pushing down is 1 atmosphere. And if we're at sea level, the atmospheric pressure is going to be greater than the vapor pressure at 60 degrees Celsius. So no boiling will occur here because atmospheric pressure is greater than the vapor pressure, which is the pressure pushing up. If we're at sea level, and let's say this time we're at 100 degrees Celsius, we have a container of water. Atmospheric pressure is still 1 atmosphere. That is the pressure pushing down. But if we're at 100 degrees Celsius, we have increased the vapor pressure. So now the atmospheric pressure equals the vapor pressure, which is the pressure pushing up. And so if they are equal, you get boiling. And boiling occurs throughout the liquid. Let's change altitude. Let's say we're 2,000 meters above sea level. Same container of water. But if we're above sea level, the atmospheric pressure is decreasing. So it's no longer 1 atmosphere that's pushing down. It's going to be less. Let's say it's 0.9 atmospheres that is pushing down instead of 1 atmosphere. So a solution will boil at a lower temperature. In this case, it will boil about 95 degrees Celsius because that is when the atmospheric pressure, which is 0.9, is going to be equal to the vapor pressure. So you will induce boiling at a lower temperature because the atmospheric pressure is lower. Boiling is a cooling process. Now, the temperature of a boiling liquid never rises above its boiling point. Let me give you an example with this graph right here. If I graph temperature versus time, over here we have water in a liquid state. So we have water over here. As we increase the temperature, you'll notice that it's a consistent positive slope as we increase the temperature, getting up to the boiling point. Once we get to the boiling point of 100 degrees Celsius, this is where the liquid gets converted into the vapor. But the boiling point of water will never rise above 100 degrees. So when you boil water, it will stay consistently 100 degrees Celsius. Only when the liquid is all gone will the vapor rise in temperature. But boiling water always boils at 100 degrees Celsius if it's still in the liquid phase. A liquid can have various boiling points depending on pressure, so we are going to define the normal boiling point as the boiling point at 1 atmosphere pressure, or 101.3 kilopascals.